At DEF CON, my team released a tool for experimenting with short-lived encryption keys on the TPM, and also a white paper discussing secure time sources and mobile computing. The tool and the white paper are linked from recent blog posts that you can get from this URL here. Okay, there, sorry about that. General Alexander, the head of the NSA, was at DEF CON last year and also a Black Hat this year, talking about the importance of engagement between the public sector and the security research communities. However, this year, government InfoSec employees were specifically asked by the DEF CON conference organizers to stay away. And more recently, of course, there's been lots of negative press about trusted computing. To me, these are both missed opportunities for engagement. We should be working on building bridges between the security community and the government and the researchers, the hackers. I'll talk more about specific threats to trusted computing throughout this talk. In any case, the government has been public about its support for secure mobile computing. For example, they released SE Android. The big takeaway for us in the commercial world is that NSA is working on mechanisms for protecting their content, their high-value content, sensitive content, from the cloud to mobile devices. So there must be ways for the private sector to do the same thing. How can we protect our businesses against well-funded adversaries? Let's review the checkered history of mobile devices. When laptop computers first appeared, they were awkward. Early PDAs were awkward, although I did like the design of the Trio. It doesn't really stand up to time, though, does it? Now half the people sitting at Starbucks have a laptop, and of course almost everybody, at least among the customer base that we're primarily talking about here, has a smartphone. And now that we can work and play in the digital world anytime and anywhere, we do. But as work moves to less secure mobile computing platforms, hackers like Lisbeth here have a new world of opportunities. After all, hackers and spies are just like the rest of us. They look for the most return for the least effort. So their focus is now on mobile devices, as we should expect. But what can be done about this? The first thing we want to do is define some key characteristics of a trustworthy machine. But the main thing we learned from Terminator 1 and 2 is that machines are sometimes trustworthy and sometimes not. Thanks. Likewise, people talk about identifying the person on an internet transaction, but it's not a person. It's a machine. And it may or may not be properly expressing the user's intentions. Given all that, how can we be sure that a remote party is telling us the truth? Desktop PCs and laptops can be configured to be relatively secure. We've learned over the years how to do that. And users can be trained. We've also learned how to do that. Some of this applies to phones and tablets, and some doesn't. For example, it's hard enough to enforce complex passwords when the user has a full-size keyboard, which my VIO here more or less qualifies as. But on phones, it doesn't work. The keyboard experience is built around autocomplete, and it's not even consistent across apps or devices. Likewise, most mobile platforms lack the system-level extensibility required by good third-party antivirus software. Still, mobile devices have a lot of untapped functionality for increasing security. So let's see how to use it. Relatively low rootkit risk is perhaps the only aspect of the phone that's more secure than the typical PC, at least right now. We all know that's very likely to change. But even now, application-level attacks have become easier. So when a mobile app or game is free, or costs 99 cents, you can bet that there's been zero attention paid to security in that value chain. You get what you pay for. And not only that, but in mobile there's a new range of risks, from geolocation, privacy loss, theft of data, theft of service. And as recently pointed out in the popular press, there are legitimate concerns about privacy when device identity can be publicly tracked. In short, it remains difficult for the device to reliably report on its current state. And that presents a risk to back-end services and to sensitive data. To get reliable information from the device, we need to get an authenticated report from a tamper-resistant root of trust. This is the purpose, as I'm sure most of this audience knows, of the Trusted Platform Module, or TPM. Again, if you'll bear with me here, just for the little intro, the TPM is a crypto processor typically implemented either as a tamper-resistant motherboard chip or as a component of system-on-a-chip firmware. Device integrity is the point of the exercise, but how can that protect the stuff that the user and the custodian of the content really care about? 2 points to consider. First, we want to measure that the device is actually running the way that it says that it's running, and the way that we want it to be running. Second, we want to ensure that only on a compliant device can I decrypt sensitive data, and only while the device remains compliant. By issuing encrypted content protected by a key bound not only to a specific TPM, but also to specific measurements on that device or in that TPM. And not only that, but also to a specific time range enforced by that TPM, we can really lock down the lifetime of that content. And we think that this is a new, interesting capability. But first, how can we determine if the device is telling the truth about its state, given the risk that's posed by bad apps, bad firmware, etc.? Well, remote attestation uses the TPM, uses the root of trust, to determine if the firmware, the bootloader, the operating system are all known good. I talked about remote attestation. You've seen other presentations about remote attestation. I have some links to previous talks of mine from my company website. In any case, what this means is that determining the health of a mobile user does require some infrastructure, mobile device, mobile user too, I guess. And it's a cryptographic dance, so there's some complexity, some things that can go wrong, but it is achievable. Nevertheless, I'm not asserting that these techniques should be used for every transaction. Currently, they're too heavyweight for that. But for securing high-value data on consumer-class mobile devices, TPM and remote attestation, basically the offerings of the TCG, are the best thing that's out there right now. It's the best game in town. And I think that that message has really been lost lately in the press. So let's dig in. With measured boot, starting with the BIOS, before each component in the boot chain is loaded, the previous component computes its hash on disk and stores it in the TPM, in the platform configuration registers, or PCRs. Then, after boot, a boot log can be retrieved from the TPM. The log includes some pretty interesting metadata. It includes some boot image hashes. It includes code signing information for making trust decisions, for example. And it includes other boot metadata, for example, whether disk encryption is turned on. So there's some pretty useful policy tools built in there. And importantly, the TPM can sign that log with a special purpose key. The server can then issue a content decryption key or authorization key bound to those measurements on that TPM. In other words, the server encrypts the content key in a way that is unique to a specific state of a specific device. When the device state changes, the measurements change, and the TPM will thereafter refuse to decrypt that key, refuse to decrypt the content. Again, we think this is a pretty sharp knife. Trust starts with the TPM and the key distributed with it. Again, this is set by the manufacturer or the OEM, along with a PKI certificate that's signed by that manufacturer. If you have a list of those, you can verify the chain of trust. But the TPM is as protected as hardware or firmware can be, given the current state of the art. So I think we need to be candid about the threats. Electron microscopes are a threat. Zero-day firmware bugs are a threat. An insecure OEM supply chain is potentially a threat. Where do you buy your chips from, right? But the important point equally is that none of these threats is new, and each can at least be partially mitigated. So let's not throw the baby out with the bathwater. However, we think that the biggest threat to the TPM right now is lack of customer demand. That has nothing to do with insecure supply chain and all that other stuff. Customers don't even know about that stuff, let's be honest. So it's incumbent upon the trustworthy computing community to demonstrate the value of these technologies in real-world scenarios in ways that normal people understand. For example, TPM 2.0 includes this monotonically increasing tick counter. This, at least, is a more secure option than the real-time clock on your PC for enforcing policy. So there's some interesting applicability that your average IT guy can actually understand here. This counter is the foundation of the work that I'm presenting here that we've been doing on secure time-bound keys. Once the client device has received a measurement-bound key from the remote attestation service, how should that key be used? Well, consider that constant reauthorization is expensive and it's really annoying to the user. For example, Kerberos uses a token that's good for, say, 8 hours. Why does it do this? It wants to reduce the inconvenience of having to reprompt the user for credentials. Users have about that much patience for that. The point is that that validity period is a policy setting that can be ratcheted down for the paranoid or ratcheted up for better user experience, let's be honest. But why not use this same technique to protect mobile data? For gory detail on how to do that, including talking about implementing a data loss prevention solution, implementing a DRM solution if that's your preferred TLA, using TPM measurement-bound keys, please see the white paper that I mentioned at the beginning of the talk. Also, to run your TPM through its paces, please check out our timed key tool. I'll warn you that the prerequisites for running the tool are a little bit steep, since unless you have a system on a chip, Windows 8 laptop or tablet that's less than a few months old, you probably don't have a TPM 2.0 device that can run third-party code. Obviously, this is a concern if you're planning on offering solutions based on this capability. But we believe that that will change in the near term. And specifically, that there's demand in here for small, high-value deployments, growing beyond that as adoption increases. My blog provides a trace of running our timed key demo using the tool. These traces are sufficiently verbose to allow you to reverse engineer, for lack of a better tool, the TPM commands that we're sending, if you're into that sort of thing. In summary, using the first 3 commands of the tool, this is basically what the demo does. First, you create a measurement-bound private key in your TPM. We make the key good for 60 seconds. Obviously, that's a nice, easy demo to do. Note that another major improvement in TPM 2.0 is that it supports elliptic curve and symmetric key cryptography. TPM 1.2 only supports RSA, and 1.2 does not support this time-based policy that really is the whole point of what I'm showing here. So the next step to running the tool then is just to encrypt some test data. And then still within that 60-second window, decrypt the data and demonstrate that you still can. Then after the 60-second window, when we expect policy enforcement has killed the key, try to decrypt that data again, and sure enough, you'll see that the TPM reports a policy violation, it's expired. The scenario would be that the user then has to reauthorize. We want to make sure that they're still trusted, that the device is still trusted, get new access to the data. With those capabilities in mind, again, how can measurement-bound keys be used to protect mobile data in the real world? So consider data accessed by trusted insiders. This is obviously a timely topic. In this case, we want to ensure that only users with trusted client machines and users who can successfully authenticate themselves, and likewise with devices that have encrypted disks, boot pins, the whole 9 yards, everything we can throw at the problem, obviously, only those people can download sensitive files from the document repository, say SharePoint or Box.com or Dropbox.com if you saw that previous presentation. By using platform attestation to enforce PIN-protected disk encryption, for example, and also hardware identity, and also a limited lifetime of the key, we're really decreasing the chance, I believe, that data can be recovered from a lost or stolen device. Again, this is the best game in town right now. But before you deploy such a system, you're obligated to consider what can go wrong. What are the threats? So let's take a step back for a second. The BIOS integrity measurements, or BIM model, defined by NIST for securing computers against rootkits. BIM basically boils down to measured boot plus TPM remote platform attestation. Obviously, depending on how you implement it, how much of it you implement, etc. Based on this, my company implemented a project called BHT for DARPA Cyber Fast Track last year. We included the data flow diagram that you see here, along with the threat model, as part of our deliverable to DARPA. Looking at the diagram, security increases from the left, where you have the end user, to the right, where you have the TPM root of trust provisioned by the manufacturer. It's the two rings on the right, the TPM and the supply chain, that we depend upon for measuring the trustworthiness of the client device. However, included in the attack surface of the TPM is all of the system-level firmware and hardware and stuff that TPM depends on. So you can consider that attack surface to be big or small depending on your perspective and on how much you trust your OEM and where they bought their chips, etc. And of course, this also assumes that your remote attestation solution is itself, competently implemented, secured, etc., and securely deployed, of course. So a few questions are raised. First, what is the risk of one or more endorsement keys being compromised from a major OEM? And if that happens, is a spoofed TPM a threat to your deployment? If so, does your remote attestation solution support blacklisting? Second, are your adversaries sufficiently well-funded to steal a specific device from a specific user and dissect the chip in order to retrieve keys from it? Because if you are such an enterprise and you're using consumer class hardware and BYOD, then it's like, I don't know what to tell you. But anyway, okay. Finally, what is your organization doing to mitigate the risks posed by stolen devices, rootkits, and bad firmware today? And would TPM usage raise the bar or lower the bar in that context? This is a great story for us. The answer is always, it raises the bar. So we believe that properly engineered remote attestation middleware can significantly narrow the window of attack on mobile data. But there's nothing that middleware can do to mitigate the risk of a compromised chipset, for example. And in order for users to be able to interact with the plain text data within their allowed policy, there is a heightened window of attack during that time. In any case, remember that the goal is to prevent the user from lying about its integrity, about the device integrity. TPM 1.2 is widely available on PCs. Unfortunately, it has not been widely used. As a result, the user experience around initialization and provisioning is relatively poor. And this can necessitate shortcuts if you're trying to deploy secure solutions in a typical heterogeneous environment. And of course, environments are only getting more heterogeneous. This problem is essentially solved on the latest hardware. So that's good news. So hopefully adoption of TPM 2.0 will continue to increase. We recommend that measured boot be used to enforce disk encryption. That's as part of any data loss prevention solution deployment. On Windows, this combination basically implies BitLocker. BitLocker has been the subject of several published attacks. Nevertheless, when properly configured, it's good protection. Note that for other TPM-based encryption solutions, including those you might implement to take advantage of the measurement-bound keys stuff that I've been talking about, many of the same types of attacks may apply, so you have to do your homework. Try to reduce the exposure of your keys. Another way to rephrase that is, try as we might, we haven't solved the key management problem yet. But we keep on raising the bar, and that's good news. Looking forward, from my perspective as a security software integrator, there are 3 questions. First, Intel has excellent developer support for the technologies we've been discussing. We've been using the Intel platform as the foundation for our prototyping. But it remains to be seen, frankly, if their mobile platform adoption strategy will be successful, with the new generation of chips, etc. Second, ARM has been slower to embrace TPM than Intel, presumably due to lack of consumer demand for that feature. But if Intel makes TPM a differentiator, will ARM respond? They might. Third, finally, can software companies successfully package the measurement-bound keys capability and similar TPM-based features in a way that is both secure and usable? Either way, as I've demonstrated, short-lived keys are a great tool for data protection, and support for TPM 2.0 is increasing. So, learn to trust machines, if only for short periods of time. Any questions? Yes?
So you teased us a little bit by talking about NSA capabilities, Tradecraft for communicating with the cloud.
I admit that's true.
And the entire conference was voted to security endpoint. But what about that cloud server? I need a TPM in the cloud server because I need it to be attested that it's what I think it is. How do we get there?
Question is I think the question is a lot about data center scenarios for TPM. There's at least one Seattle-based startup that is working on basically the scenario they were working on, as I understood it, is before your blade or appliance or whatever gets a job from the controller, it would do some sort of platform attestation. Now, of course, you run into some challenges where that may be okay if you have like these really virtualized environments where you can kind of move workloads all over the place to kind of reset one set of machines every 8 hours, let's say, and then run jobs there and then move them. But that obviously is harder if you're running a workload on a single piece of hardware for 6 months. I mean, your image can get wildly out of whack during that time, as you know. And likewise, there's not yet a good story around virtualized TPM. So to your point, there's some challenges.
There's a lot of work on it.
There's work on it.
I'd love to have a VPN whose key was reset every 60 seconds.
Yeah, and yes, exactly. And we'd love to be able to revalidate the platform, within a pretty narrow window, and still have the experience be seamless to the user. I mean, we both know the technology isn't quite there yet.
So Dan, talk a little bit about where you see the role of trusted execution in this space going forward. Because in the DRM context, there's 2 steps. One is distribution security, which is what you talked about, the first unlock of the file.
Yeah.
And then the second step, which is how do we protect from Snowden putting those files on everything else and exiting the building with it, whether it's USB or CD-ROM or whatever, right? How do I assure that the clear text image of that file
Yes, yeah, right. So question about, completing the story of the DRM. Customers ask us, let me say, a similar question, which is essentially, hey, this is a really powerful protection, this is really powerful protection at boot time, but once the user is logged in, it's Wild West again, and we're trusting the antivirus solution. What are you guys doing about that? And, to me, the best answer is right now, well, it's still a work in progress. You kind of still have to trust your antivirus solution. Trusted execution, I think, quite frankly, to me, is again, it's a similar story where we're still having to trust endpoint security software that is maybe running a kernel, but it certainly has user mode components to do policy enforcement. And that's not as good a story as what you get at boot time from the TPM. So there are gaps there. You look dissatisfied with that answer. I'm dissatisfied with that answer.
So to me, we're a small group. The most interesting thing that was shown this year was at RSA, Intel demonstrated in their TXT environment the ability to render an image that could not be seen by any debugger or any infrastructure principally. They really were writing directly to the video memory with TXT. And so they had created a secure channel to video. So in theory, if you were to apply the temporal key unlock tied to that mechanism, you could have content that would have been rendered that would be really incredibly difficult for an administrative hacker on an endpoint device to have gotten the content of the data without a photograph of the screen.
Yeah, agreed. So I think still, of course, there's still an integration challenge then of, can you deploy a solution with lockdown laptops so that users can do secure read-only access to PDFs? Acrobat has Acrobat's attack surface. And then can you deploy a solution that allows people to do read-write access via Word? Word has Word's attack surface, right? And how do you kind of incorporate those giant feature-rich applications into your secure execution viewer? I think that's coming. I just don't think we're there yet. Yeah. Okay, thanks a lot, guys. Appreciate it.